Hello. In this video, we will be looking at some problems relating to power and energy. We are looking at objective number 3, which is to know and be able to use the definitions of power and energy, and objective number 4, to be able to use the passive sign convention to calculate the power for an ideal basic circuit element. The first problem that we're looking at is assessment problem number 1.5. This problem states, assume that a 20-volt voltage drop occurs across an element from terminal 2 to terminal 1. So let's draw this out. What does that look like? We have our basic element here. This is terminal 1, and this is terminal 2. So it says a voltage drop from terminal 2 to terminal 1, and it's a 20 volt drop. And the current is 4 amps, and it enters at terminal 2. So our current would look like this, and it is 4 amps entering at terminal 2. Specify the values of V and I for the polarity references shown in this figure. Okay, I have moved this figure down, so let's take a look. This is our defined voltage and current direction, voltage polarity and current direction, and how does it relate to the figures below? Well, let's look at the first one. The polarity of voltage is defined as a voltage drop from terminal 1 to terminal 2, which is the opposite of our defined voltage polarity. So since it's the opposite, we would change the sign. So in this circuit element, it would be a 20 volt, minus 20 volt in the direction polarity given. Okay, current, on the other hand, is defined as entering terminal 2, but in circuit A, it's entering terminal 1. So again, this is the opposite, so we would define our current for our circuit A as minus 4 amps. All right, now let's go to the next one. Our voltage polarity, again, is positive at terminal 1, negative at terminal 2, which is the opposite of our defined. So we change the sign, and that would be minus 20 volts. The current, on the other hand, is entering terminal 2, and which is the same as what we have defined. So the sign of our current remains the same. All right, let's take a look at circuit C. In circuit C, our voltage is negative at terminal 1 and positive at terminal 2, and that polarity lines up with our defined polarity. So our voltage remains a positive 20 volts with this circuit element. Let's take a look at current. In circuit C, the current is entering into terminal 1, but our defined circuit is the current is entering into terminal 2. So we will change our polarity or our sign for the current. All right, let's take a look at our last circuit element. Let's see, I haven't used pink. With the last circuit element, our voltage polarity is defined as negative at terminal 1 and positive at terminal 2, which lines up with our defined voltage polarity. So we would have a positive 20 volts. If we look at the direction of current in the circuit of number D, it lines up with the same direction as our defined current. So our current value is a positive 4 amps. So that takes care of A. Now B says, calculate the power associated with the circuit element. Now we know the passive sign convention tells us that whenever the reference direction for the current in an element is in the direction of the reference voltage drop, such as here or here, then we can use the passive sign convention, which is P equals positive VI. So you have a couple ways of doing things here. You could, let's use purple here. You could use the equation associated with each configuration, or you can convert to the passive sign convention and use one equation, P equals VI. And I'm going to do that because it's just another exercise in understanding polarity of voltage and direction of current. So in our first circuit, the current is in the same direction and the voltage polarity is the same as circuit A. Circuit B, the current is in the opposite direction. I'm going to change the color here. Let's do purple. So our current, sign of our current would change, and the polarity of the voltage is the same between the two elements. In circuit element C, the direction of the current is minus 4 amps, and the polarity of the voltage is opposite, so we will change the sign. And in circuit D, the direction of the current is opposite, so we will change the sign. And the polarity of the voltage is opposite, so we will change the voltage. Now you will notice that in all four circuits, once you changed it to the passive circuit element, they all have the same value. And we can use one equation. So using that equation, P equals VI, we have P is equal to minus 20 volts times minus 4 amps, which is equal to plus 80 watts. Okay. So that takes care of B. C asks, is the circuit element absorbing or delivering power? When a circuit element is absorbing, our power is greater than 0. Delivering power the value for power would be less than 0. In this case, our value for power is positive, so the circuit element is absorbing. Okay, I just wanted to make note that when you are watching the videos in the text, the older text use the ideal basic circuit element that looked like this, but they are both the same. They are both ideal basic circuit elements, and they pretty much are the same deal there. Okay, let's look at assessment problem 1.7. A high voltage direct current transmission line between Oregon and California is operating at 800 kilovolts and carrying 1800 amps as shown. Calculate the power in megawatts at the Oregon end of the line and state the direction of power flow. Okay. They have set up the defined polarity and defined direction of current, and if we apply this to each circuit, our voltage would in California would have that polarity, and the direction of current is entering into the positive terminal. On the Oregon end of things, the polarity is like this, and the current is leaving the positive terminal, or we could say it's entering the negative terminal. So we will take advantage of the passive sign convention at the California end of things. So at the California end of things, we would use P equals VI, and our voltage is 800 times 10 to the third volts, and our current is 1.8 times 10 to the third amps, and that would give us 800 times 1.8 is 1440 times 10 to the 6 watts, and they want us to express it in megawatts, so that's pretty easy to do. Megawatt. Okay, now, and this is a positive value, right? And we're doing things from California's perspective. So in California, energy is being absorbed. So that means Oregon must be delivering if California is absorbing. So in Oregon is delivering 1440 megawatts to California. And that takes care of this problem.